In section 3.1, we learned how to compute the derivative using the limit definition, but that's actually very long and tedious. So what we're going to do in 3.2 and 3.3 is we're going to introduce some rules for computing derivatives so that you don't have to use the limit formula. So let's look at this first rule. It's called the constant rule. And the constant rule just says that the derivative of a constant is 0. So if I was going to take the derivative of 4, the derivative is 0. And then we have two versions of the power rule. The power rule says that when you take the derivative, you bring the exponent into the front and you subtract 1. So if I was going to take the derivative with respect to the variable x of x squared, that would be equal to bring the exponent in the front, so it's 2x, and minus 1 from 2 gives you x to the 1. Now in this section they're saying that n is any integer. However, you can use the fact that n can be any real number. So this property is going to come up a little bit later, but you could use that now. So for example, if you're going to take the derivative of x to the 1/2, you could bring the 1/2 in front times x, and then minus 1 from 1/2 would give you a negative 1/2. So you're free to use that now. So this makes sense, the next power rule. If you take the derivative of just the variable x, it's going to be equal to 1. And that's because it's the same as saying the derivative of x to the 1 power. By the power rule, we would bring the 1 out in front, and this would be x to the 0. Anything to the 0 power is 1. The constant multiple rule just says if you have a constant number, you can pull it out into the front of the derivative. So if I was going to take the derivative with respect to x of 2x, that's equal to 2, because I can just pull that derivative out in front, times the derivative of x, which is just 1. So this becomes 2 times 1, which is just 2. And then we have the sum and the difference rule. The sum and the difference rule just says when you're taking the derivative and you're adding or subtracting functions, you can just compute the derivatives separately and then do the addition and subtraction at the end. So why don't we go ahead and work some examples out. If we were going to find the derivative of, in example 1a, of f of x equal to negative 3x to the 2/3, then the derivative, I can take that negative 3, which is a constant, out in front, and then just take the derivative with respect to x of x to the 2/3. So that's going to be negative 3 times, and here the 2/3 comes out in front. X to the 2/3 minus 1 would be a negative 1/3. And then I could see that the 3's are going to cancel. So I have the derivative of f is equal to negative 2, and typically when you have a negative exponent, you make it positive by dropping it into the denominator. So I'm not sure if your MyLab will have you do that extra step. Sometimes it's okay if you keep a negative exponent and they won't mark you off, but sometimes they want you to have positive exponents only. In the next example, we have y is equal to 3x to the 7 minus 5x plus 7. So if I take the derivative of y, I can ignore the 3 because it's a constant, and then just take the derivative with respect to x of x to the 7 minus, ignore the 5, take the derivative with respect to x of x plus, and then the derivative of a constant will end up being 0. Now I'm splitting this up using those properties. Eventually you don't have to do this step. So this is going to be 3 times 7x to the 6 minus 5, derivative of x is just 1, and then we have a plus 0. So this would be equal to 21 x to the 6 minus 5. So that would be the derivative of y. In most cases, we're going to be using y or f or g to denote a function. But sometimes you might see this notation in example 2a. Notice it says find the derivative of v with respect to the variable t. So the derivative of v with respect to the variable t is the same as finding the derivative of f with respect to x. The problem is this is a product of two functions of t, and none of those properties or rules discusses the product. So unfortunately, I can't take the derivative just yet. I'm going to have to multiply this out before I could take the derivative. So that would be 3t to the third minus 15t squared plus 2t minus 10. Now that I have it all multiplied out, now I can take the derivative. So the derivative of b with respect to the variable t will be 9t squared. And notice that I'm not writing down d over dx on every single piece. It's okay if you don't. I just did it for the first few examples so you get the idea. Minus 2 times 15 is 30. This becomes 30t plus 2. Okay, so again, you don't have to show all those steps. So the derivative with respect to t of 1 over t squared, again, that doesn't fit any of the rules. I have to write this so that it's t to the negative 2. And then I can use the power rule to find the derivative of v with respect to t, which is going to be negative 2 times t to the negative 3. And if we need to write this with positive exponents, this would be negative 2 over t to the third. So the next example that we're going to look at is going back to this idea of tangent lines and equations of tangent lines. So let's just say this downward facing parabola is my function f. So if you notice at the point 1, 2, we have a tangent line. And we're all really familiar with tangent lines now. So there's also another type of line that's going to pass through that same point 1, 2. And it's going to be perpendicular to our tangent line. So a line that's perpendicular to our tangent line is what we call the normal line. Okay, and it has the property that when it intersects the tangent line, it intersects at right angles. In example 3, we're going to look at some function, which is x cubed minus 3x plus 4. And in part A, we want to find the equation of the tangent line. So that would just be an equation of a line. It's going to happen when x is equal to 2. So remember, we need a point and a slope for the equation of a line. So if x is 2, and I put 2 into my function y, I get back 6. So I have a point, 2, 6. I need the slope. And then the slope of the tangent line is just our derivative. So what we're going to do is we're going to compute the derivative y prime using the power rule. So that's going to be 3x squared minus 3. And then we're going to evaluate this derivative when x is equal to 2. So the slope of our tangent line is going to be 3 times 2 squared minus 3, which is equal to 9. So now we have a point and we have a slope. We can write the equation of our tangent line, which would be y minus 6 equal to 9 x minus 2. And typically we want to simplify this and write it in the slope-intercept form. So just solving for y, we get y is equal to 9x minus 12. So that would be the equation of the tangent line when x is equal to 2. Sorry. So let's look at part B. In part B, it says, for what x is the tangent line horizontal? Well, the tangent line is horizontal when its slope is equal to 0, because that is the slope of a horizontal line. And since the slope is the derivative, that means we're going to take our derivative, 3x squared minus 3, and set that equal to 0 to solve. So we'll get x squared is equal to 1. So x is equal to plus and minus the square root of 1, which is just 1. So these are the x values, positive 1 and negative 1, where the tangent line is horizontal. So let's look at part C. In part C, we're supposed to find the equation of a normal line. All right, it's going to pass through the same point, 2, 6. So we just need the slope. So you have to remember that when we talk about perpendicular lines, their slopes are negative reciprocals of each other. So a perpendicular slope means what we're going to use is, it was a positive 9 for the tangent line, so it's going to be a negative 1 over 9 for the normal line. And that's it. The equation of the normal line is y minus 6 equal to negative 1 over 9 x minus 2, which we again would simplify into a point slope form. Okay, so if I add 6, I get y equal to negative 1 over 9x plus 56 over 9. Something that we can do when we compute derivatives is we can compute derivatives 1 time, 2 times, 3 times, infinitely many times. Remember, the derivative is a function. So we can keep taking a function and computing the derivative over and over again. And that would be the last thing that we'll talk about in this section. We'll talk about the higher order derivatives, like a second derivative or any nth derivative. So if it's a second derivative, notice that the notation is two of these little accent marks or hash marks. Or you can, in parentheses, put a 2 for second derivatives. Or you can say the second derivative of our function with respect to x. And then there's some other notations as well. What you do not want to do is you do not want to say f of x and put a 2 on the outside. That's not a derivative. That's an exponent. It says f of x times f of x. Okay? So that's not what you want to do. Okay? And then for any nth order derivative, you would just use n. So let's look at how we would apply this in example 4. So we have this function y, and we want to find the 5th derivative and the 100th derivative. So first of all, y prime, and this is just using the power rule, is going to be 4x to the 3rd minus 3x squared plus 2 times 3 halves, the 2's would cancel. So I'd have 3x minus 1. The second derivative, I'll use 2 of these accent marks, would be 12x squared minus 6x plus 3. I'm getting lazy. I don't want to do 3 hash marks, so I'm going to put a 3 here for the third derivative. And that would be 24x minus 6. The fourth derivative would be 24. And now the 5th derivative, the derivative of a constant, is just 0. So when you think about this, as I keep taking derivatives, 6th derivative, 7th derivative, and so on, the derivative of 0 is always 0, which tells me that the 100th derivative is 0. Okay, so that's it for this section. In the next section, we'll look at another rule that we're going to add on. So these are pretty short sections.